Yeah, let's open the floor for questions. Yeah, Arpit.
Am I audible?
Yes.
So, um, the example that we discussed in module 110, uh, I'll send a screenshot as well. But yeah, so in the transform program, uh, so in the transform program, we are assigning I equal to 0 after we check uh, for the condition. But like in the for loop, it has been assigned before. So like if n were less than equal to 0, then I equal to 0 would be assigned on the left side but not on the right side. So like it should be outside of the if statement, right?
Okay. Yeah, that's a valid point. Yeah, so actually, if I was being used later on, then it needs to be assigned before the if condition. Yeah, I agree. I agree.
Right.
Thank you for pointing that out. I guess, in this example, I'm just assuming that I is a local variable, local to the for loop. Just like in C, you can say for int I equals 0. So it's just, it really doesn't matter. But yeah, you're right. I mean, if I is getting used after the loop, then I needs to be initialized before the if condition, because irrespective of whether the n is greater than 0 or not, I should be equal to 0. Right. Absolutely. Okay. More questions, thoughts? Sonu?
So I have a question about the same module where we discussed about a unconditional branch, and so in the first the for loop, we see that it's not a fall through branch and it's an unconditional branch.
Okay.
The edge from ai equal to t going back to the condition, which is I less than n.
Sure.
Yeah, so I was just trying to understand the difference between the two, unconditional branch and it's not a fall through. It is unconditional because it is going into the middle of the program, or how do we actually differentiate between the two?
Oh, an unconditional branch. So the difference between a conditional branch and an unconditional branch is that a conditional branch depends on some condition, and depending on that condition's truth value, it's going to either go jump or it's going to fall through, right? So that's a conditional branch. An unconditional branch always jumps to the target. Okay. But fall through is basically like a no op, right? I mean, that's the default behavior of my CPU abstraction, that I execute something and then I go to the next instruction, right? So the difference between unconditional branch and fall through is that fall through doesn't require an extra instruction. That's the default behavior. An unconditional branch requires an extra instruction. I mean, that's the only difference, really. Does that answer your question?
I see. Yeah, I think I'm probably still not able to understand or see the extra condition in this edge. So AI equal to t, after that, will directly move to that.
Yeah, there is no condition. That's why it's an unconditional branch. But
Yeah. So
there's an instruction, right? You need an instruction in your instruction scheme. It says jump or branch to the head of the loop, right? So that's what we are saving here. No?
I see. So I get that. I mean, there's no condition. I agree. What is the additional instruction that you're talking about? Maybe I'm missing that.
So I guess so the difference between the before and after of the two cases is that in one case there is an extra instruction, and the other case there's one less instruction, right? This is something that I guess you pointed out in your summary yourself, right?
Right.
You agree with that, right?
Yes, I agree with that. Yeah.
Yeah. So I mean, and the instruction that we really got rid of was the unconditional branch, because we was basically able to just get rid of the unconditional branch, because we just structured such a way that the unconditional branch could be removed, and just the fall through mechanism of the CPU could basically take care of the control flow wherever required, right? So can you repeat your question? I mean, I'm just not clear about
Okay.
it. Yeah.
Yeah, sure. So I think I probably did not explain it correctly. So I'm fine with conditional and unconditional branches. I understand the difference because conditional branch will have to take into account the condition.
Right.
But I think my question is the difference between unconditional branch and a fall through. So I think in this case, there is only one exit path from AI equal to T going to I less than N. There's no other option. So we still say that it's an unconditional branch. But in some cases, even if there's one path, we say it's fall through. So
Okay.
what
I see.
exactly is the
Okay.
difference between the two?
Okay. I think I understand the question. Unconditional branch is required when you jump from a program point to a program point different from the next instruction.
Okay, yeah, I think
In the static code order, right? I mean, it's not because it's a loop, I cannot just put the head of the loop after the last instruction of the loop, right? I mean, I have to make a jump to get there. And so that's why I need an unconditional branch. But in general, if it kind of follows, if it was possible to basically reach that place just in a static code order, then I save that branch, right? So that's the difference between fall through and unconditional branch. Unconditional branch basically jumps to a PC value, which is different from the next PC value, the fall through PC value.
okay, got it.
In the static code order, yeah.
I see. Okay. And then actually, I have a related question to this. So then I understand we save on one branch instruction, which is like a good thing. But I'm just trying, maybe I do not know about it, but I think the idea is saving one instruction helps, but how does saving a branch helps more? So what is going on in the background that saving a branch will help us more?
Okay, so in general, branches are a little bit more expensive than regular instructions, more so for conditional branches than unconditional branches, because what happens is, let's say you take a 5-stage pipeline, right, with the typical 5-stage pipeline that you study in your computer architecture course. Then if it's a conditional branch, then you don't know which condition it's going to go, and so you don't know what to fill your pipeline with. So the conditional branch is going to go 3 steps, but you don't know what to kind of follow it with. You follow it with this or that. Unconditional branches are better in that sense that you know what to do and so on. Still, actually, unconditional branches basically have an argument which say where to jump, and architectures would have structures that would try to predict where the branch is going to jump, because the two PC may become clear only after, let's say, the decode stage, and until you don't know what the decode stage is, you cannot get the next instruction. So for example, if it's fetch, decode, execute, then until the decode hasn't happened, you don't know what to fetch next.
I see. Okay.
On the other hand, for every other instruction, you don't need to decode to fetch the next thing. Right? So that's for a 5-stage pipeline. But in general, even for, so by the way, your typical computers, like the laptop that you're using to do this conference, is likely not just a 5-stage pipeline. It's much more complicated than that. But even there, the same kind of issues arise. Basically, the problem is that there is a control dependency, and so you don't know. You need to know what is the next instruction to execute, and because it's a branch, it'll take slightly longer than an arithmetic instruction or something like that.
Right. Okay. Good. Thank you.
Yeah, that's a good question. Thanks. Okay. So I wanted to point out that this loop inversion example, I remember that I think it was Arpit who asked once that, can I do loop invariant code motion across a for loop? Uh, and you said that partial redundancy elimination subsumes loop invariant code motion. But recall that partial redundancy elimination is kind of enforces that you cannot have any extra computation on any other path. But then if you hoist something above a for loop, then so let's say there was a computation called z equals x plus y, and this entire computation was loop invariant, and this was inside the loop body, and this was a for loop. Can I put z equals x plus y outside of the for loop? Does partial redundancy elimination allow that? And the answer is no, because on the path that you don't enter the loop at all, you are in the original program, you are not going to do z equals x plus y, but in the new program, you would do z equals x plus y, and that violates my principle of partial redundancy elimination, that on no program path is any extra computation introduced. So what's the answer? I mean, how did we, in light of the material that we have studied this week, what do you think is the answer to this question? I mean, this would be a drag, right? I mean, if I cannot hoist x equals y, z equals x plus y, which is loop invariant outside of a loop, that would be, that would be a significant drag on my performance, just because I have this crazy rule that I don't want to introduce extra computations on the non-loop path, for example. So what's the answer to that now? Yeah, Arpit.
Right. So when we transform the loop, so after the after the condition, a true branch, and before the body, we can just add a basic block in which we can like add all the invariants, and
Right.
like these were already being had to be executed once, so
Right.
there's
Exactly.
no additional.
Yeah, absolutely. So because of loop inversion, you now have a place where you can put this loop invariant computation z equals x plus y without having any path on which you are doing extra computation, because now you have converted the for loop to a do while loop, and now you can hoist instructions which are loop invariant outside of the do, just before the do, and it would be okay, because anything that is within the first iteration of do while is always going to get executed, and so now you can put it before the do, and you would be still respecting your partial redundancy elimination properties. Okay, so that's so here's a very very illustrative example of how one transformation enables other. It's not just, we have talked a lot about how one DFA analysis helps another, how one analysis based DFA based transformation helps another. But here, loop inversion is not a DFA based transformation. Okay, loop inversion is using something else. It's using the property of a loop. And now loop inversion is now enabling some DFA based transformations like partial redundancy elimination or lazy code motion. And so by the way, I mean, loop inversion is one of the very staple transformations that a compiler would do very early in its optimization pipeline, because it just enables so many other things. We just saw an example. Okay, so it's not just about saving a branch, but it's also about enabling more stuff with this transformation. Okay. And by the way, even saving a branch is a big deal. It's a loop, so it's probably going to execute millions, billions of times, and saving a branch would at least save you on, if it's going to execute a million times, then saving a branch would at least save you like order of 100,000 cycles, and an order of 100,000 cycles, is a significant saving right there. Okay. Okay, more questions. Somehow there are not enough questions today, which is rare actually. Everything is very clear, huh? Okay. Okay. Let me think of something. All right. So we have looked at loop peeling. We have looked at loop inversion. Loop peeling basically means that I peel out. I mean, so the word is very suggestive, right? I peel out, like it's like a, it's a circle, and I peel out 1 or 2 or 3 or 4 instructions and put them at the top. And something like this. I mean, can somebody kind of think about? So before I ask the question, there's another category of transformations which are called loop unrolling. Okay, so the loop unrolling is basically the idea that you have a for loop which is doing I++, and it just executes one iteration of the body inside the loop. Unrolling is going to just do 2 iterations or 4 iterations in a single body. All right, so it just unrolls the loop inside the body. So it's like, body, body, body. So if I look at the pattern, it's cont body step, and then back. But I just unroll it. It says cont body step, and then back. All right. So what I've done is I've increased the code size, but now I have saved one more branch, perhaps, right? I mean, now you may say, okay, but however, save the branch because in the middle there is a jump out anyway. So there's a check in the middle, and so it may not have really saved the branch. But in many cases, you may be able to say, oh, I'm sure that, for example, if you knew that n is an even number, then you know that you can unroll the body twice inside the in the unrolled loop, right? So this is called loop unrolling. Is this clear, or do I need to explain this more? Okay, so this is called loop unrolling, and this is different from loop peeling. Right? Loop peeling is basically taking a body and putting it before the header. Unrolling is taking the body, making a copy of it within the loop itself, right? And also adjusting your loop, the condition. If so basically, because you're doing the step twice, that's, you don't need to adjust anything. But sometimes you may be able to get rid of the middle condition, because let's say you knew that n was even, and so because n is even, you use this property to basically just get rid of the middle condition, and that's a saving, isn't it? Because you just saved one branch, you have saved one conditional branch, which is significant. But there's one bigger advantage to doing loop unrolling, and that is that you have increased the size of the body. And now you can do, now what happens is there is more stuff to play around with in terms of optimization. Okay. So for example, your step is saying I equals I plus 1, but now there is I equals I plus 1 again. So there are two steps, I equals I plus 1. And what can you do here? You can just say, oh, it's I equals I plus 1, and then I equals I. Let me just say I equals I plus 2. Okay. That's simple. Similarly, you are saying, let's say AI equals 0. So now let's say the size of an element in my A was, let's say, 4 bytes. So let's say an integer. So it's 4 bytes. So I'm setting 4 bytes to 0 in one iteration. But now, because I unrolled it, and I see that the first instruction is AI equals 0, and the second is AI plus 1 equals AI plus 4 equals 0. Well, it's AI plus 1 equals 0, which basically in the memory means the a plus 4 into I, and then a plus 4 into I plus 1, they get to 0. And what I can do is I can replace these two different memory writes with a single memory write, which is an 8-byte memory write in one go. Right? So even though in the original code I'm writing 4 bytes at a time, and I'm writing that twice for 2 iterations. Now in the unrolled loop, I can write it once and this does do 8 byte, right? Assuming your machine supports 8 byte writes, which a 64-bit machine will support. Okay, so that's another advantage of loop unrolling, and it's another example of a loop transformation that is, that I want to emphasize is not really, DFA based. It's actually using the rule. It is now we are discussing a topic which is different from DFA, which is, understanding the structure of the program and exploiting that. And one of the most important structures in a program that we typically write is a loop. The other point I wanted to make was that, look, loops are very important because they are very common. What is a construct in a programming language like C or Java or anything else that you can come up with, which will produce a cycle which is not a loop?
Go to.
Okay, go to. Anything else? Okay, yeah. So the answer is no, there's nothing else. Okay, it's only goto that can produce cycles that are not loops in high-level programming languages like C, C++, Java. Of course, in assembly, there's branch and all that, which is very similar to goto. But apart from goto, and in fact, higher level programming languages now have stopped supporting goto as well, right? I mean, it's such a, and most of us, I hope, are not using goto. Gotos are considered a bad practice, bad programming practice. What does this mean? It basically means that, any logic that you want to encode, it is possible to encode without using goto. In other words, any logic you want to encode, it's possible to encode with only natural loops. I mean, you don't need any other kinds of cycles. Natural loops are sufficient for almost all logic. I mean, you can sometimes optimize your code such that GoTo would have given you slightly better performance than if you coded it using for loop or while loop or do while loop or repeat until loop or something like that. But it's not I'm not aware of any major difference between non-GoTo code and a GoTo code. Any example of a major difference between code to code in terms of performance? Okay, so that's why, and that's the reason. And so this GoTo less programming is also called structured programming. It can in some kind of context, and so we encourage people to write structured programs in any case because they're easier to read, easier to understand, easier to write, of course, and also the side advantage is that they're easier to optimize. Okay, and actually that is that may be a common theme you would find across compilers, which is something that is easier to write and read and understand is also easier to optimize. Okay, and so that's thankfully there's no trade-off here that something is easier to write but it's harder to optimize, so we want you to use GoTo. No, that's not happening, so that's good for us. Okay, all right. The other thing I wanted to say was, see, some of these optimizations kind of transformations are kind of interrelated. So yeah, Jay, your question.
Yeah, so I just had one question about natural loops. Do natural loops have multiple exits? It has a single entry point, but can it have multiple exits as well?
Yeah, absolutely. A natural loop can have as many exits as you like. Yeah, absolutely.
So like a break statement or something, which is very common.
Exactly.
So a follow-up question
break is like break is structured programming, right? I mean, it's not violating us. Yeah. Okay.
Something like loop unrolling and stuff like that, where we just copy things, like we are copying the body once again. So let's say the body has a lot of break statements and a lot of conditions. Like break statements generally have conditions that, okay, if something happens, break out. So if you are unrolling in that particular thing, like, aren't we like increasing the number of branch conditions, which like the number of okay, so it would like,
you're never increasing the number of branch conditions, you're only increasing the code size, but from an execution point of view it will never be anything anymore. It can only be less. All right, the only downside of doing unrolling or peeling or even inversion is that it increases the code size. And you may ask, does it matter if I increase the code size? And the answer is, to a certain degree, it does not matter. And that's why these transformations are so common. But beyond a certain degree, it starts mattering. For example, I cannot just unroll my loop, 128 times or 250, some large number like 1,000 times. Even 128 is a big number, but in some contexts, actually today compilers do unroll that much. Okay, so I mean, it's not completely unheard of, but I mean, in that order is basically where the limits are reached. And why are these limits? Who defines these limits? Why are these limits meaningful? Any answers? I mean, why do you think there is a problem with increasing the code size beyond a certain degree?
Like the RAM, the program should fit the RAM and the caches and everything.
Yes, it's about the caching, right? I mean, RAMs are typically so big today. I mean, the gigabytes, right? Codes are typically on the order of megabytes. So it's not like the memory is going to get exhausted anytime soon. I mean, you can even unroll a lot and memory is not going to get exhausted. But it's the caches that start becoming a problem. And most processors will have separate instruction cache and separate data cache. I mean, like many processors, for example, the Intel processor. And that's for a reason, because instructions have a different access pattern than data, and so you want to kind of separate the two so that you can exploit both different types of access patterns and optimize for them separately. And so if you unroll a lot, then what happens is your instruction cache may start behaving you know, may have more misses than you want, may undecidedly. Okay, and so that's the only thing you need to guard against. But loop inversion is a very safe optimization. You know, you're only adding maybe one or two or three instructions here or there. I mean, that's almost zero cost. Okay. Um, Loop unrolling, you can do, you know, people do unrolling so compilers would typically have some kind of heuristics to say the body is small, it's okay to unroll, or the body is the body has enough opportunity to optimize after I unroll. So there'll be some heuristics of that sort. For example, I just gave you an example of AI equals 0. Now here the compiler should use the heuristic, okay, you know, it looks like I should be able to optimize when I unroll. That's another kind of important thing, right? You unroll and there's no opportunity for optimization, then it was a wasted effort, and you also paid extra code size, right? The other thing is, of course, can I predict that the number of iterations will be even or a multiple of 8 or something like that? Now, another thing that is typically done, if I can't say that n is a multiple of 8 or something like that, what I can do is I can peel the first. So I don't know whether n is a multiple of 8. So what do I do? Let's say n is not a multiple of 8. So what do? I basically peel off n mod 8 iterations in the beginning, so that now n minus n mod 8 will be a multiple of 8. Okay, and now I can do unrolling and I can save branches. And then when I kind of peel out n minus n mod 8, I need, you know, it's not just, you know, I just, n minus n mod 8 is not a constant, it's a variable, it can even be 0. So what I need is actually a peeled out loop, a header loop, which is going to just go from 0 to n minus n mod 8, and then another loop which is going to go from 0 to n minus n mod 8, right, or something like that. But the second loop will have number of iterations that are multiple of 8. And now it becomes super easy for me to unroll it. I mean, it's always easy to unroll it, but the good thing is that when you unroll, I don't need any checks in the middle. And so I have saved that many. I've saved, let's say, 7 conditional branches, and that's a big deal, right? Assuming that the compiler has confidence that the loop is going to execute many times. The first loop, which was just n minus n mod 8, is a very small loop because it's going to only execute less than equal to 8 iterations. But the main body of the loop is going to execute n minus n mod 8, which is order n iterations, and n can be million, billion, something like that. Okay, and now I've also saved that many branches, right? So I've saved order n branches, that n to 8 pretty much branches, and that's pretty good, right? Plus, I have now created a body of code that I can kind of reorder and put together and sometimes combine into single instructions. And these are all very consequential transformations. The downside is I have increased my code size, of course. Arpit?
Yeah, so I was thinking that like there's also that we can emulate gotos using switch case, right? Like the do and duff device.
See, switch is not a cyclic thing, na? It's all acyclic. Even with Duff's device and all that, right? It's all acyclic. So it's okay. I mean, it's not the same thing as goto, right? I mean, I cannot go back using switch.
But in like if we just take Duff's device, then we are using the switch case, we are jumping into the middle of the loop body, right?
Mm-hmm. Oh, so, it's not a. Is it? I don't remember the Duff device. I don't remember. I don't think it's a loop, right? Okay, give me a second.
It's a do while loop with a switch case. Right.
Aha. Okay. Right. Now I have it here. I have it. I see. Aha. Yeah. Okay. So this is also bad programming. Yeah. This is also unstructured programming. So yeah, you're right. I mean, apart from goto, C has this weird semantics of switch, and so switch can also produce unstructured programs. Okay.
Right.
Yeah. That's a good point. And if you're curious, for everyone else, just search for Duff's device, DUFF apostrophe S device, DEVICE, and you'll be able to see an example. Later on in the course, which we call them reducible graphs. And so Duff's switch and goto can produce irreducible graphs, but everything else, and even like very stylized use of switch, right? Most people, 99.99% of people will not use that way of writing switch code. I mean,